We'll do one more example, again, to demonstrate that the question is what's driving the sampling distribution we will eventually use. The length of human pregnancies from conception or birth varies according to a distribution that is approximately normal, with a mean of 266 days and a standard deviation of 16 days. So we're being described a distribution of pregnancies with a mean of 266 days and a standard deviation of 16 days. And this is my population of length of pregnancies. That's what this concerns. The length of a pregnancy is independent of length of any other pregnancy, and let the random variable y measure the length of a pregnancy. Again, I jumped the gun, should have been reading. Let's call this y. If we sample 100, so now we're going to sample. We're sampling 100. But now on the other side, what is it that I'm going to land? Depends on the question. What am I doing with 100? What is the probability that 11 or less, I'm sampling 11 or less. This sounds like counting. Okay, I'm counting something. Sample have a length of 250 days or less. So what I'm counting is the number of times I witness a data value that has a pregnancy that is 250 days or less. This is the criteria that I'm counting. Because of this, it sounds like I'm sampling 100, 11 meet this criteria. This is really about the question is about sampling distribution of proportions. Because what I'm going to do with these 100 values is figure out how many meet my criteria. So really, this is the sampling distribution, the sample proportion. Fantastic. It looks like my p-hat in question is 11 out of the 100, or 0.11, 11%. What is p? The probability of observing one pregnancy and whose days are 250 days or less. Well, I need to find it, just like in the previous question. Notice nowhere here is it given to me, but success then is this, 250 or less. This is P, the chance of that happening. What is the chance of this happening? This right now, if a pregnancy lands there, this is labeled success. So this is a normal distribution, so let's figure this out. I need to figure out what success is. So let's do this. 250 minus 266 divided by 16. What is that? For the quick calculation, it's like it's -1. Okay, -1. So what's the chance of getting a single value to be less than 250 days? That's the equivalent of saying that my z-score is less than -1. So I'm going to come here to GeoGebra, choose less than, type in -1, and I get this value, 15.87% approximately. So that's what this value is. That is the chance of one pregnancy lasting less than 250 days. That's success, or less, 250 days or less. Again, equality here means nothing because it's continuous. So it turns out that E of p hat, which is P, is 0.1587. This will be true regardless of the sample size. But I have 100 here. Do I meet the criteria? Well, again, can I draw a normal curve? And again, I need to check this criteria. So one thing you might start to realize is that statistics involves checking a lot of things. Do we meet certain conditions? And this is true. We do. We have to meet conditions in order to use certain processes. 100, that's going to be 15.87, clearly greater than 10. And if that's true, I'm not going to calculate it, but 1 minus 0.1587 is clearly greater than 10. Again, around 16 are greater than 10, so this will be around 84 are greater than 10, so 83 something. So that's fine. So now that I've done this, check the condition, so meet central limit theorem, distribution of p hat is approximately normally distributed, at least its shape is. So I'm going to be able to draw this. And what I want is 0.11 at 11% or less. Again, we just made this into a nice number so we can do this almost in our heads. So I'm looking for 0.11 or less. What's the chance of this happening? Again, this was not given to us. This meaning the probability of success, the population proportion was not given to us, but we can get it. Okay. And the way we get it is figure out what our criteria is. Once we figure out what the criteria is, we ask, what's the chance of observing one instance on one observation, that criteria? And it turned out to be this, 15.87%. Now we just come over here and go through the motion of, okay, what's the chance that my proportion, sample proportion, is 0.11 or less? That as a z-score is, have I calculated the z-score? No. So now I'm going to calculate another z-score for this other situation. Again, notice the formula for the z-scores. We're going to end this, but we are going to see that it has always the same type of rhythm. Our measurement, the center of our measurement, divided by our sample size. So enter all that in here. So I'm not going to be able to do all this in my head. That does happen. I just erase my fraction, so I can get it back pretty quickly. Here, 1 minus 0.87, and then close it. I'm gonna hit the division key. It's okay. I'm gonna erase that. I'm gonna highlight this. Then hit the division because I don't want to do that. Something I could do is just come over here and put big open parentheses and divide by, and then type 100. No. And there we go. Negative 1.3328. Now I come over here. I'm still looking less than, right? Yes, I am. Then drawing my picture allows me to just, as I'm doing these calculations, make sure I don't not losing track and writing my symbols, writing everything down. You should be doing that. So I'm expecting to do that in exams. It's part of the grade. 0.0913. So it's about 9%. Not that unusual. Again, notice I'm just a little bit beyond one standard deviation. Is this unusual? Actually, it turns out that no. So look at this. This is beginning of the realm of unusual. It's going to turn out. And notice how many standard deviations we were away at, 1.58. So just going a little further around, I think 1.7 something is when we get the realm of saying, yeah, it's unusual. But here we're at 1.33. Yes, it's not common, but we're not ready to call it yet. Very unusual. So let's end up with the following. We've looked at the z-score formula, which is a way of standardizing information. Very common thing to do in statistics. We'll end the course with another one called a t-distribution. And again, it's the same thing, so don't get too hung up on it, but same process. They all look about the same. So here's the one we first started out when we looked at the normal. Again, we use the symbol mu and sigma, but I could have easily done this. Use this notation instead. Then we looked at means. So all of a sudden, the measurement turned from a single value to a mean. Then this became the mu of the means and sigma of the means. And I guess I could also, this is the way it's usually presented in most books, but if I want to be consistent, I could put a little subscript here saying the variable name is X, the standard deviation of the variable name X. Here, it definitely is needed to make sure we understand that this is the mean of the sample mean. Again, I could have also done something like this. You won't see this in textbooks a lot, so this is just habit of writing things. But there we go. It's a z-score for the means. And now we've done the following. Here's another formula. But again, we recognize that this one has a little more few moving parts. Notice we have to write down, this is the standard deviation of the mean, the sample mean. This one, because of the parts it has, we can actually calculate the inner parts. And we could have just easily also have written this. And now by writing this, we're masking some of the detail. But this one, just by its nature, it's very, well, I don't know, open, I guess. This one by its nature could be a lot more complicated. So that's why sometimes we just mask it saying, look, somehow this is the mean of the population, this is the standard deviation of the population. So you have your three z-scores for the three situations that we've encountered so far.